Spectre. Okay, thank God. All right, so I've given this talk before. You may have seen an iteration, but I think this is the most public forum that I've given it in. Okay. I'm also booting this in because I thought my talk was tomorrow, but it's apparently not. So in the middle of our tower of abstractions, at least in the middle, for the purposes of this talk, we can think of machine code as the middle abstraction. So the instruction set architecture is what programs actually run on physical machines. You don't have to understand x64 machine language, but this is something that I stare at almost every day. But above the machine, there is a source language, of course, which you're all involved in implementing. So this happens to be C++, God, unfortunately. So we take our source language and we compile it to the instruction set architecture, and then we don't have to worry about all the offsets into memory and the registers and all of that. But of course, there's an abstraction below the instruction set architecture, which is actually how it's implemented in hardware. There are no such things as registers at the level of physics, so instead we have to implement registers and instructions using circuits. Normally, these things, these bars in between, these lovely green bars using my wonderful slide making skills, those are supposed to be abstractions that you cannot see through. But the problem, so why do we even have abstractions? I think you probably all know this, so I'm preaching to the choir. But the source language gives us this abstraction that's easier for us to reason about as humans. It's closer to the language that we use to communicate with each other. We now have new concepts that are easier to deal with and easier to get right. So we have loops and functions and objects and things like that. We don't need to see all the implementation details, so we don't have to see this giant array of cells in memory. We don't have to deal with registers and things like that. It makes it portable too, because there are many different machines, many different instruction sets. So we would like to run on these many different machines and have the same program without any modifications. But one of the great things about an abstraction like this is at least you're supposed to be able to run untrusted code. Since that code can really only interact with the abstractions that we give to it, it shouldn't be able to see the details underneath. In particular, if we have a language or a virtual machine that enforces memory safety, then we can run this code in a sandbox. The problem is that, as you'll see in horrific detail throughout this presentation, is that this is not actually true anymore. There's going to be details that leak through this abstraction boundary. That's the subject of this talk. But just to also give you an idea of why there's an abstraction on the other side is that hardware fundamentally cannot implement the abstractions using matter and energy. We actually have to use physics and physical circuits to do that. This ISA boundary in the middle gives us backwards compatibility. So if you're familiar with x86, it's been around for 40 years. The instruction set architecture has grown, but it hasn't really changed in those 40 years. Yet the microarchitecture, so the hardware implementation, has changed radically. Not only because we have lots more transistors, but there's lots of new hardware techniques to make it go faster. That gives the hardware designers implementation freedom to implement abstractions in a different way and make it faster, make it more energy efficient, give more memory and such. It allows evolution of the microarchitecture over time. And the idea is that the optimization hardware should not be observable because this abstraction, this green mirror here, should not be something that we can see through. Fortunately, this isn't really true. We kind of always knew that, but we never really thought that this was a security problem because you can observe optimizations just by timing the code that you're running. And actually, the new thing about Spectre is that optimizations are actually leaking information in ways that violate security boundaries. Okay, so who has never seen a control flow graph before? Thankfully, none of you. Okay, so this is, our abstraction of what machine code looks like. You have basic blocks, and you can organize them into a graph. Anytime you have a split in the control flow graph, that's like a branch. Many branches are normal application branches. If some condition, I'm going to do this. But when we get to an implementation of a language that is supposed to enforce memory safety, it may insert checks. So the implementation may generate machine code that has safety checks. So normally, most programs are well behaved. Going out of bounds in an array is typically a bug. So there would be some safety check inserted into the code that almost always passes. Branch predictors, which are trying to learn the history of your program and the likelihood of which direction a branch will go, of course, are going to learn to predict this branch to go successfully through the access, because you're not normally going to go out of bounds and signal an error. So from the hardware level, the branch predictor basically has an idea that with high probability, we're going to go to the right for the first branch and to the left for the second branch. The problem is that if an attacker or a buggy program feeds a bad input here into a safety check that would go the wrong way, is that actually the branch predictor is happy to run ahead and just assume that this safety check is going to pass and go ahead and execute the access. And of course, if that input is bad and it's out of bounds, we may actually go out of bounds of an array, for example, and access off the end. Of course, hardware designers knew this, so this is supposed to be completely unobservable. The microarchitecture keeps all of the state or potential state that will be changed in buffers and called speculative buffers or reorder buffers and things like that. And then it will throw away any of potential side effects from mispredicted branches, roll back and execute the error code. Unfortunately, there's state in the microarchitecture which is not in the architectural specification, and that can actually be changed as a result of executing the access. So we call that mu state or microarchitectural state. And so now we have the problem that a program which knows this can actually leak information by executing an access and then leaking some information through the microarchitectural state. So nobody kind of realized this until about 2 years ago, even though this is like a 30-year-old concept, which is actually pretty amazing, and we're all embarrassed. So there's actually lots and lots of microarchitectural state. This is everything that I could think of, and there's probably even more. So I'll just run through these because you'll see later that many of them could potentially be side channels. So think about the implementation of virtual memory. So the operating system gives you the illusion of a large address space, which is backed by physical memory, which is not actually true. It only gives you physical memory for the things that you're currently touching. That's implemented with virtual memory techniques such as page tables. So those page tables are in the operating system. They are cached in the hardware, but you don't see them from an application perspective. Maybe we can store information there, or maybe they could leak information there. The actual RAM chips, and Mario talked lots about NVRAM, but also DRAM has state in it. So DRAM actually has rows. The way it's organized in the hardware is there may be a row of bits, which is, say, 1,000 bits long or 1,024. Of course, it's a power of 2 because hardware people love powers of 2. But that DRAM line buffer means that that line of memory is actually faster to access. So there's some state there, which line is there. Of course, in Spectre land, we typically use instruction and data caches as our side channels. Those are super huge. So an L1 data cache is 32 kilobytes, but L3 might be 40 megabytes. And it stores a small amount, cache line blocks, which are essentially small copies of memory. And the occupancy of the caches is our side channel, is the information that is not visible at the application programming level. But there's also caches for those page tables. So what's called the translation look-aside buffer, the TLB, is actually a cache of page table entries because it's too expensive to go hunt through the page tables in memory every time. And actually, if you look into the design of those, they're actually pretty complicated. They actually have multiple levels of caching in the TLB in modern chips. And then we mentioned the branch predictor. Of course, it has some state. It has tables. These are essentially hash tables, looking up a branch's address and finding a potential target. There can be lots and lots of bits of there. There could be thousands of entries in a modern branch predictor. There's also another cache, too, for return addresses. So as you make procedure calls and returns in your program, instead of actually going to memory and loading the return address, there's a tiny little cache, which may be 16 entries, which is managed as a stack, which actually tracks the call and return behavior of your program so that the CPU doesn't need to even go to L1 cache to find out where to return to. So that is a potential side channel as well. There's a cache of the actual instructions themselves, so the CPU, at least x86 CPUs, don't actually directly execute x86 code. They translate it internally into a simpler RISC-like language, and there's a cache for those micro-ops. There are other things which are behind the scenes too, which may control the processor's operation. On Intel, those things are called model-specific registers. There may be a dozen of those or a couple dozen of those. And the state of those registers may impact how your program runs, even though you can't see them. So there's some state hidden there. But even deeper in the CPU, every time you write to memory, those writes actually go into a store buffer. That's also to implement speculative execution, so that any store which has been speculatively executed doesn't actually change memory until you know for sure that any branches that guard it were actually taken. That's called the store buffer. That's a potential side channel. One thing which is actually I didn't even know about until about 1.5 years ago is a thing called a memory disambiguator. So this is a mechanism in the processor which is trying to figure out whether dynamic loads and stores actually depend on each other, whether they're actually aliases. And if they're not aliases, it's happy to reorder memory accesses. And so there's actually some predictions involved. And there's a whole field of research in the hardware community about memory, on memory disambiguators that goes back 20 years. Bet you didn't know that. CPUs also scale their frequency in order to save power. There may be many cores on a chip. They can't all run at maximum frequency. Even if they did, they would consume so much power, they might melt the chip. So processors actually dynamically scale the cores depending on their workload. So the current frequency at which the core is executing is also state as well. CPUs also have execution ports. These are actually the things that execute the little micro-ops. With which things are in what execution port, the occupancy of the units is actually state as well, and those could potentially be side channels. Lazy FPU state, so on Intel chips, the SSE registers, those may not actually be saved when you do a context switch in the operating system. They may be saved lazily. So there's essentially a bit in the processor. Are the FPU registers valid or not? And if not, you'll get a fault to the operating system to lazily save them and restore from another process. So that actually turned out to be a side channel and a vulnerability. We can keep going down. Every single bus, every single buffer in the CPU, the occupancy and the throughput available there are all essentially hidden state. So I mentioned all these things, but most of them are not interesting for this talk until I get to the end. But I want to mention Spectre is more than just data caches. It really doesn't have anything to do with data caches. Data caches are the side channel for leaking information. They work fantastic because data caches are super fast, super big, and they're randomly addressable. That means that you can store lots and lots of bits, and they work perfectly for siphoning off information in the world of Spectre. Okay, so I'm going to go through an example. You've probably all seen this by now, just to make it crystal clear how this works. So we're going to use the data cache as our side channel to store information about some value that we're not allowed to access or shouldn't be allowed to access. So imagine that this code is actually, I wrote it in source code so we don't have to deal with machine code because that's a lot of details. But imagine that this was a bounds check emitted by a JIT compiler. So every array has a length, and the index is actually controlled by the user or the attacker. Maybe they're not a bad person, maybe they're just lazy and they have a bug in their program. So the index is the thing which the program controls. Everything else is essentially generated by the compiler. So if the user passes in an index which is actually out of bounds, then this check is going to fail. We're going to actually execute the else branch. We imagine the else that is like throw an exception or something like that. But if it is in bounds, we're going to access some array. This is a user array, the one that's actually called array here. I used orange to indicate that this value might actually be a secret, because if we're out of bounds, then we're accessing some random memory off the end of the array. But we can't actually see that value anymore because if the CPU mispredicts and executes this code when the index is not in bounds, it's just going to throw everything away. But what we can do is we can use that value, particularly we can use a low order bit of that value, and we can access one of the lines of this timing array. So cache lines are typically 64 bytes on most hardware these days. So we can use the bit, which we're not supposed to see, to access one of two lines, and that will indicate what the bit's value is. So in speculation, it's going to execute all of this code, and it's going to touch either timing 0 or timing 64, depending on what that bit was. And then even though all of this is thrown away, the cachedness, which one of those lines is fast, is going to survive speculation. Yeah. So memory is this huge array, for example, 4 gigabytes or 64 bits worth of address space. It's divided up into lines, and those lines are typically 64 bytes, and those are the unit which caches deal with. So if we touch one line or another line, the cache will either have one of those lines in memory or the other. Does that make sense? Any questions about that? Is this pretty clear? Okay, so when we deal with a language like JavaScript, or even Java to some extent, it's not just bounds checks that could potentially be a problem. In fact, there are lots of safety checks which the JIT compiler will insert into the machine code to enforce safety conditions. So if we just step back and make that a little bit more abstract, just imagine that we have some condition that establishes a safety property for the program, like a number check, like whether a value, which is dynamically typed in JavaScript, whether it's a number or an object, if that check is mispredicted, maybe we actually use a number as an address. And then now you have essentially a gadget that can access any part of memory because we can control the bits in a number. Also, this can happen because in JavaScript, objects have dynamic shape. They can change shape. They can essentially get longer or have more properties. And there are checks for the shape of an object which are implemented as branches. And branches can be mispredicted, and you can use an object of the wrong shape and then potentially read memory that way. Also, JavaScript functions, you can pass more or fewer arguments than they expect, so there's going to be branches in the code eventually to check how many arguments do I have. So if you can get that check to mispredict, maybe you can use an extra argument or a junk argument to execute some gadget. Also checks for global variables and other runtime checks. There are dozens, perhaps hundreds of types of checks that V8 would emit. All of them are potentially vulnerable. And what that really means is that essentially any high-level language feature which you enforce with branches in the code may be vulnerable to this type of misprediction and information leak. So we analyzed this, and we realized that ultimately what the attacker would want to achieve is reading from memory that they're not allowed to access. And any one of those checks that we emit, if they can mispredict it in the right way and feed data to it in the right way, you can build a gadget that allows you to read memory, arbitrary memory in speculation. So we call that the universal read gadget. So there are many ways to construct this, but ultimately it gives you this procedure. In any typed language, you can write this procedure, which may be super complicated, but you can feed it a 64-bit address, and it will execute a read, disclose the value of that read into side channels, and read the side channels, and then give you the value back. That's pretty bad because as language designers, we assumed that our languages were memory safe, and this breaks all of that. Okay, so in order to do this, I'm super proud of the colors in this slide. I made this myself. But we're going to need to traverse 9 orders of magnitude to understand just how tiny the timing differences from optimizations in a CPU can be. So just to give you an idea, it's essentially impossible to visualize a billion, so I'm going to have to give it a couple tries here. So imagine that on the right-hand side of this slide, we have a second. That's a second worth of time. Every time we move to the left, we're actually adding a factor of 10. So every one of these is a factor of 10. So we do that 9 times, and we end up at a billion. To think about the difference between 1 second and a billion seconds, This talk is about an hour, so that's about here. That's about 3,600 seconds. A day is somewhere in the 80,000 range. A week is somewhere close to 1 million. A lifetime is somewhere around 2 to 3 billion seconds. So imagine 31 years and 1 second. The difference is one factor of a billion. So let me give you another analogy, because that one is difficult to sink in. So just take a look at your arm. So that, let's say 30 centimeters, that's about a foot. Everybody hold up your finger and look at your fingerprints on your finger. If you see there's little ridges on your fingerprint, the distance between two ridges on your fingerprint is about 1 millimeter. Now imagine that the entire Grand Canyon fit in one ridge of your fingerprint. Okay, so that would be a factor of like 300, right? From 30 centimeters to 1 millimeter. The entire Grand Canyon is in your fingerprint. Now imagine in the Grand Canyon is you again. And you look at your fingerprint, and you look at the ridges, like the distance between two ridges, which would be 1 millimeter. That difference between you in the Grand Canyon in your fingerprint and your arm is 1 billion. It's huge. So now we're going to traverse all those orders of magnitude to look at how big the difference between 1 second and 1 nanosecond is. So now we've shifted the entire scale down by 9 orders of magnitude, and now we can actually start to think about how tiny these timing differences are in a computer system. So, ironically enough, or perhaps conveniently enough, the resolution of the clock that you get in JavaScript on most platforms is on the order of a couple of microseconds. That's about the same as the difference between 1 second and the length of this talk. So L1 cache is super fast. Hitting L1 cache is about 3 cycles on a typical chip, so that lands over here in about 1 nanosecond range. So if you have a 3 gigahertz chip, that's about 1 nanosecond for 3 cycles. L2 is about 12 cycles, so it's about 4 times slower. L3 might be in the let's say 40 to 100 cycle range. DRAM is getting into the hundreds of cycles. If we're worried about the difference between hitting L1 cache and going to DRAM, the timing difference, it is actually much lower than the resolution of the clock available to us. So at first, it would seem like those tiny timing differences that might result from touching one cache line or another cache line would not seem visible with the resolution of timer that we have available. Unfortunately, this is a completely programmable system, and you can create clocks that are even higher resolution, and you can find clocks that are higher resolution. So even though this performance.now may have a resolution of 5 microseconds or 1 microsecond, you can actually create other timers that may have higher resolution or different resolution. So there's this wonderful paper from about 3 years ago, before Spectre was known, about all the timers that you can get just in the web platform. So it turns out actually you can create timers from doing CSS animations, which is pretty amazing. You can essentially tell the difference between one frame and another. That's lower resolution than performance now, so 16 milliseconds. So that's not so much of a problem, but you can do other things. You can create workers, which are essentially threads. And you can send messages between them. And if you have high performance message passing, you can create a timer this way. So you can also create microsecond resolution timers using messages. There's a couple of other ways to do that. Down here, these techniques called interpolation and edge thresholding. If your timer is, let's say, based off a higher resolution timer by just lopping off some low order bits, you can create a higher resolution timer by just running a loop and waiting until you see the clock edge change, so the value of the clock, and then you can essentially use your loop to count how many iterations it takes between those two clock edges, and then you can interpolate the resolution. With that, actually, you can get down into the nanosecond range, and now it's starting to get dangerous. You can start to see individual cache misses. So if you can do one of these interpolation techniques, then you can already get there. But you can also construct a timer directly using shared memory. So this is actually really simple. You have a thread that just increments a counter, and then you have another thread that reads the counter, and that actually executes fast enough you can have nanosecond resolution.
As a question, when the Spectre meltdown came up, one of the things the browser people did was to limit the granularity of performance of dollars in JavaScript. Yeah. Does this mean that this was effectively useless?
No. I will talk about that in detail. Excellent question, because it's coming on the next few slides. So the first thing that we did is reduce the resolution of performance now. And of course, we had some advance notice of Spectre. We thought through many of these things. We knew that this was not going to be a complete mitigation. So lowering the resolution of the timer means that it's more difficult to detect these differences, but it's not impossible. And we did this in a way, so performance now, the way it was implemented before, was just take the nanosecond resolution clock, drop the lower bits, and give them that, which is, of course, susceptible to this thresholding technique. So instead of just lopping off the low order bits, you essentially randomize the low order bits. So this way you can no longer reliably detect the clock edges, and the resolution we give you is really the resolution which is available to you. Another thing that we did, which was completely unprecedented for the web platform, is there is an API to create shared memory from JavaScript, shared array buffers, which are basically giant byte arrays that are accessible from 2 workers. We just disabled them. We literally crippled the web platform. We looked at usage counters of how many web pages actually use this, and we decided, because this was like a massive security threat, we just removed the API, and overnight, gone. We've since brought it back with other mitigations, but this was all the browser vendors in backroom smoky discussions, all freaking out, deciding that this needed to be done. And the technique that we used to reduce the resolution was using uniform random jitter, as I mentioned, essentially randomizing the low order bits of the clock that you get back. So this is part of defense in depth. It's not a complete mitigation, because, as you'll see in the next coming slides, just timer mitigations alone are not adequate. Any questions about that? Yeah.
I don't really understand how, I haven't read the manual about Spectre, so I don't understand how it's related to time.
Okay, so as I mentioned, the cache lines are essentially a way to speed up memory accesses. So the way the cache works is that anything that you've accessed recently is faster than something that you haven't. So if you can access something in speculation, then you make that thing fast for the next time. And if you can access one of 2 things based on a bit, then you can measure which one of them is fast. That's how time gets into this. So it's essentially a timing channel.
So adding jitter to this measurement and so on seems also quite costly. So is it still possible to add jitter without actually taking so much time that it takes longer than these 100 microseconds?
Oh no, so we don't actually literally wait. We just add some randomness to the measurement that you get. So we don't actually change the cost of reading the timer. Yeah. Okay, so we saw how we can do timer enhancement through edge interpolation, or edge thresholding and interpolation, resolution recovery. But you can also do another thing. So this is getting a better timer, and this is making the actual information leak have a higher time difference. So we can do both if we're an attacker. Just to show you the code for this, like pretty much anyone who can write JavaScript would be able to do this. You just have a global mutable variable. You have a dedicated timer thread that just counts in a loop. And then from the other thread, you just read the counter before and after, and you subtract the difference. You can get to about 3 nanosecond resolution with high precision this way. And if that doesn't work, what you can do is you can have multiple timer threads, and then you can actually, because maybe the timer thread isn't running all the time, maybe it's running on a different core, and you're pinging cache lines back and forth, you can have multiple different timers and choose one dynamically. So you can make this pretty sophisticated so that you get the guarantee of a high resolution clock. Okay, so now I'm going to talk about amplification. So fundamentally, timing differences that arise from these tiny optimizations in the CPU are very, very small. As we saw, they're on the order of nanoseconds. But since it's a programmable system, we can actually do something to batch up many different timing differences and make a bigger timing difference. So this is just one way to do it. So imagine that we have a secret bit, and we're going to encode the secret bit into the cachedness of memory as we did before. So instead of just using one of two lines, we can use a huge set of lines. So let's say that if the secret bit is 1, we're going to touch all of the lines A0 through AN. And if the secret bit is 0, we're going to touch B0 through BN. So this would be the mechanism where we write the bit into the timing domain. And then to extract the bit out of the timing domain, we measure how long it takes to access all of those cache lines. So now the difference is not a single cache line, but n cache lines. So however many cache lines that we can fit into the cache itself, that is the maximum difference that we can create using the secret bit. So this is ultimately going to be limited by the cache capacity. But thankfully, caches keep getting bigger and bigger and bigger, which makes them more and more useful for exactly this. What we found is that if you completely fill up L1 versus L3, you can get up to about 600 microseconds difference. So if you're able to create a gadget where you reliably can get to the secret bit over and over, then you can touch as many lines as you want, and you can get essentially 600 microsecond timing difference, which is much larger than the 100 microseconds to which we've changed the timer resolution in response to Spectre. So you can essentially go over any clock resolution. Yeah.
If you go this far up in the time scale, you won't be able to extract much bits, right?
Correct.
So you would make just a lifetime of...
Right. Yeah, so you reduce the bandwidth of the covert channel, but you don't eliminate it. So you can essentially read half a bit per clock cycle. So if you make the clock cycles bigger, then you reduce the total throughput of that channel, but you don't eliminate it.
Yeah. So, isn't it limited by how many instructions are expected to be executed? Same. It's also limited by how many instructions are expected to be executed. Like, it is all sorts of things that may not be executed in sort of time.
Right. So the number of instructions that you can execute in speculation limits the size of your gadget, right? But you don't have to execute the entire gadget in one speculation. If you're able to read the secret bit more than once, then you can do multiple rounds of speculation, and you can disclose one cache line at a time. So the entire gadget doesn't have to totally fit in the speculation window. I will also mention that you only need a couple of instructions for one of these gadgets, and the reorder buffer on a typical CPU may be 200 instructions, so there's plenty of space. It's really dependent on how long it takes the processor to resolve a branch, and you can do various things to make that longer so that you get a bigger window. Yeah.
So we are also, since we're mispredicting, then the next time, so what happens to the branch predictor? Will it say, okay, next time we actually have to, I don't know, evaluate and then decide where we're actually going and not speculatively execute? Because if you're doing this many times over, then maybe the branch predictor will change its behavior and say, no, we're not predicting that, but we're actually doing something else.
Right. So branch predictors learn over time. So if you're relying on a branch to be mispredicted, it may learn and then predict that you shouldn't go there. So this is where you, this is where you may try many, many times, and then let's say 1 out of 100 times, you flip the sense of the branch. So because the code that leads up to the speculation gadget around here is totally under your control, so you can try to scramble the branch predictor in all kinds of ways. In practice, branch predictors are really, really, really complicated. So hitting a perfect misprediction is hard. So you do something where it's difficult for the branch predictor to adapt. Yeah. Okay, so it's not just that we can fill up the entire cache with lines of A or B, we can actually do better to get arbitrary amplification. So imagine this. This is same kind of situation. Suppose that we can read the secret bit multiple different times. Depending on the secret bit, we will either read A or B in speculation. So this part happens in speculation, and this part happens outside of speculation. So speculation either makes the next read fast or slow, and then we can actually put our loop around the entire thing. So now we get a timing difference, a little timing difference every time we execute this, and then we can just execute this as many times as necessary to amplify that difference to be larger than our clock resolution. So that we successfully did this, you can totally make a difference of 1 second for a bit. So this basically means that no matter what resolution you set the clock to, it's always possible to create a timing difference larger than that. All right, so what are we going to do about mitigating this? So we put our heads together. We worked with people that work on Clang. We worked with the other browser vendors. We worked with essentially everybody that we could pull into this effort to deal with this problem. Maybe we can do something in the JIT to emit some special code so that even if the user code or the attacker code goes out of bounds, it's not speculated through. So maybe we can somehow disable speculation because this branch is really important for safety. So there is actually an instruction on x86 processors, which was absolutely not designed for this purpose, which has the side effect of maybe kind of sort of disabling speculation, at least according to Intel's recommendation, and not to go after them. But lfence, which is essentially a memory ordering instruction, has essentially the properties that we want, even though they're not written down in any manual. If you execute an lfence, it essentially has the effect of not doing speculation into this branch. So that means that basically the processor will wait to resolve this branch before it ever executes this code. It all sounds wonderful. Depending on completely unspecified microarchitectural details, sounds a great way to combat microarchitectural information leaks. Problem is, it costs you a lot of performance. So if on the Octane benchmark suite for JavaScript, which is very heavy on optimized code, this is like a 3x slowdown. This is essentially like taking 20 years of compiler research just off the table, like overnight. This was essentially, we did not think that we could ship this because the performance overhead was too much. Thankfully in WebAssembly, because there's essentially one type of bounds check, and that bounds check is already on something super, super big, we found a way to do this with just adding a mask. So WebAssembly memories are always in units of pages, and they're big enough that if we pad them to the next power of 2, it's kind of not a big deal. We can also, and there's only really one of them, so the bounds check for WebAssembly would be generally a comparison against a constant. If we also add a mask to the next power of 2, that means that even if this branch is mispredicted, we're going to strip off the high order bits of the user level's index, so they can only go out of bounds by a little bit. They cannot go past the next power of 2. And then we just add in the memory allocator enough extra space so there's nothing at the end of that power of 2, which means that it's safe to completely mispredict this branch. You will never go off the end of your memory because we're always masking out the high order bits of the essentially untrusted index. And the good news is this only costs about 15% of performance, which is also not super awesome considering that we would kill for 15% of performance in our compiler backend. But this is good enough to ship.
And can you go back a slide?
Yeah.
So what's the 2.8 times there? So 2.8 times of what? Overall performance?
Yes.
Performance of this branch?
Overall.
How is that explained given that it's down the misspeculated path?
Say
So the fence is in this case. Oh, no, sorry.
Yeah.
No, I'm just restless.
15% overhead. So now we can think about extending this idea to other types of safety checks that would be compiled as branches in the code. And so the general pattern is that you will imagine this is code emitted by the JIT, and the condition is some safety thing that we've introduced, bounds check, number check, anything like that. So what we can do is just not rely on branches really to enforce the safety property, because the processor just kind of ignores them in speculation. So in addition to computing the condition in order to do a branch, we also compute the condition as a bit mask. So either 0 or -1 in this case, and we call that the poison. So if the condition is true, we will get a -1. If it's false, we will get a 0. And then we use that poison to essentially destroy the information that comes out of a load. Again, so if this condition is 0, we shouldn't ever execute this at all, but the poison will be 0, so any information that we loaded will be completely cleared out. It doesn't matter if the processor executes this code with a mispredicted branch, it will not actually have access to the information, because it will be destroyed. So what that means is that the JIT basically has to introduce some extra code in various places. In particular, in the prologue of a function, we have to initialize the poison. In every branch, we have to contribute to the poison. So you imagine you may have nested conditions. We compute one poison, which is like the sum of all of those conditions. So we essentially have computed in data flow all the conditions which guard a particular piece of code. And then for every load, we have two choices actually. We can either destroy the address going into a load or the value coming out of a load. We chose to do the value coming out of the load just because it had better performance. Yeah.
Why does the processor continue executing code once it realizes that the condition is 0? Why does it keep speculatively executing in the wrong branch?
It will generally roll back as soon as it knows that the condition is false. But that may take a long time, because this condition might actually take a really long time to execute.
Right. The way to think about it is that there are two independent things going on here. One is that the arithmetic engine, which is doing the arithmetic, is a completely separate thing going on. At the front end is deciding what to execute. And the two have to communicate, and that takes time. And so it takes a while before the information is discovered to ripple back and go, oh, we went the wrong way, unwind everything.
Right. So just imagine that this condition takes arbitrarily long. Maybe the condition was actually a load from memory, and that was not in the cache. So you're going to take 300 cycles to actually get the value from memory. And while you're waiting for that, go ahead, just execute the code. Yeah.
What I mean is that if you are in a condition, why isn't the processor speculatively supposing that it's 1 and then computing? Like, how is it that we are executing a branch where we did 1, but we computed was the value 0?
Right. So let me just back up a bit. So just imagine the branch predictor doesn't look at data at all. It's just like it sees this if, and it doesn't even know what registers are. It just predicts that it's going to execute this code, right? So the data doesn't matter at all to that. So it's going to just start executing this with whatever happens to be in registers. So your question really is like, how can we go through here if we've not actually computed the condition, right?
No. It is, my question is, in the second line inside the if, we use the value of the condition, right?
Yeah.
So to actually have a value for poison, we need to know the value of the condition. And why would we ever execute x and 0 instead of just backtracking? Because we know, if we know that poison is 0, we know that we are in the speculative branch of solution.
Right. So essentially, by this being arithmetic that needs a value, processors today, cross your fingers, do not come up with speculative values. So it actually has to compute the condition. So you essentially are waiting for the condition.
Okay, yeah. So you will never actually execute leak of 0.
Right.
Okay, yeah.
But if you actually wait to have a value for condition because you require that from poison, doesn't that mean roughly that you
That's not quite true. You don't speculatively execute the data flow chain that comes from condition. All the other stuff, there may be other instructions in here that don't have anything to do with this condition, that don't depend on this condition. Those can totally be speculatively executed, including code after the branch and all of that. So you essentially only slow down the actual data flow path from this condition to loads.
Yeah, so actually you rely on the reordering, right?
It's the register renaming, which is data flow dependencies. Yeah.
So, just one last question. Was this way of running things, why would the load be speculatively executed? Because you have a dependency on the return value of the load.
Yeah.
Which is poison, so you will not
You're right.
execute afterwards, but you would still, like, speculatively execute
Right.
load.
Yes, right. You're right. In this version, the processor may actually execute the load out of bounds, but we can't use any information from it. This is why I mentioned there's a choice. We could actually put the poison in here so that the load won't execute because it doesn't have an address yet.
But you don't care about the value, you just care about the fact that it ended up in caches first.
No. So the value is the thing which is out of bounds, right? And the
Oh, okay.
yeah. Okay. Any more questions about this? Okay, so it gets worse. So processors also have predictors for indirect branches. So you think of a virtual call or a switch on, which is implemented with a table lookup. So this may look, so I'm going to use JavaScript source code to make this a little bit clearer, but imagine we just had a call to some function which is a value, like it's a first class function. So we don't know actually where that's going to go until runtime when we have a value for that. So now we have to look at the details of how indirect branch prediction works in the processor. So as it turns out, these are also approximate predictions. So for a call site where this call to F occurs, there's actually a lookup in a hash table. Where have I seen calls from this site go before? And if you have a prediction, I'm just going to go there. Well, because that lookup is actually approximate, there's going to be some potential that this call site is aliased with another call site. By aliased meaning that we end up in the same hash table entry in this indirect branch predictor. Turns out that hash table is actually very simply implemented. On Intel, they only look at the low 32 bits. I show 16 here just for illustration. But they only look at the low 32 bits of the call site to find a bucket entry. And if they find a bucket entry, then they use the bucket entry's low 32 bits, combine that with the upper 32 bits of the actual call site, and come up with a prediction. What that means and how this is vulnerable is that because of this aliasing, an attacker can actually execute code in a completely separate part of the program that happens to have the same low 32 bits for its call sites and train that call site to go wherever it wants. And now, when we execute the victim call site, which we may never have executed before, it will pick up a prediction which is learned from somewhere else in the program. So what that means is that we can essentially cause a speculative control transfer from one place in the program to literally anywhere we want, any machine instruction that we want. Anyone see why that might be bad? So what that means is the processor executes control paths that do not exist in the original program at all, cannot possibly exist, which means that they can jump to any machine instructions they want, which may look exactly like a Spectre gadget. And what's worse, it may look exactly like a Spectre gadget which doesn't have any mitigation that our JIT compiler has emitted because they jumped over the mitigation. So this essentially defeats all the stuff that we just did for variant 1. That's why it's terrible. And why it's such a big risk. But it's not a completely lost cause. We can do a little bit to mitigate this, to make it more difficult. So let's go back to the example. We have this potentially vulnerable indirect call. A mitigation that we actually implemented for various parts of V8 is actually, what we do is reuse this idea of a poison, but now we make this poison actually dependent on another argument to the function. So let's say the original target function was t. What we add is an additional argument to t, which And all normal execution paths should be equal to t. So whenever we call a function, we always pass it itself to itself. And then in the beginning of the function, we add a branch. We always add a check to compute this poison. If t is never equal to its argument, then the poison is going to become 0, and we're going to use poison as we did before and destroy all information. Yeah.
This is the last one. Is it t?
Oh.
Tn poison equals Tn?
Correct. Yes. Sorry for the poor choices of colors. Yes, exactly. Okay, so what that means is that now, whenever we do a call here, also there's an F here. So now whenever we do a call, we always have to pass the function as an argument, which means that if an attacker is trying to call some random function speculatively, they also have to manage to speculatively pass the function's same address, otherwise the poison will destroy it. Yeah.
We're actually reasoning in terms of assembly here, right?
Yes.
So technically, you can jump anywhere in the function and not necessarily in the prologue of the function, right? Yes. You just have to figure out how to fill the register with the correct value.
Correct, yes. So it's not impossible. So if you were really, really smart, maybe you could find out exactly where you want to go, and you could pass the right data value too. Except we completely control all of the registers, and we steal a register from the entire program where they could not possibly put a value that they want in there. So we picked one of the 16 registers on x86 that's the poison everywhere. And the only time that poison register is ever manipulated is by poison instructions. So you can't load random stuff into poison or into this TN, so you can't defeat that mechanism. Does that make sense?
Well, this poison register must be manipulated at some point. So if you start from a valid location and then speculatively jump somewhere, the poison should be 0 at this point, right?
Yeah.
So the poison should not poison the speculative execution because you skipped over the poison updates instructions.
So the poison is globally maintained in the entire program across calls as well. The only place where you could actually change the poison register is from the C++ code in V8, which we don't control. At least we don't control Clang, generating code. So you may be able to get values into that register by executing some C++ code and having it jump into some dynamically generated JIT code. But from JIT code itself, JIT code never manipulates poison except through these poison updating instructions. Does that make sense? It's kind of like a custom. Yeah.
So all these variants of poisoning, could this be possibly solved by some sort of like hardware language? Is that the information code, or is that?
I don't trust hardware. But yes, yeah. Okay, so it gets even worse. So this funny memory disambiguator, I didn't just bring it up on a lark. It's super interesting to discover an entire field of research which I didn't know about in hardware design, but it turns out to be a security vulnerability, and that's a problem. So this completely invisible thing, which none of us actually knew was there, turns out to be a problem. Okay, all the things that I just talked about with variant 1, variant 2, also what was called variant 3 or meltdown, the kernel leaks, all had to do with branch prediction. Out of order execution, superscalar execution didn't come into the picture. But with variant 4, now that lovely, beautiful mechanism comes into the picture. Of all the variants that are out there now, including I think the ones from last week, this is the only one where you need to have out-of-order execution to actually see it. Okay, so going back to our view of branch prediction, so we have this path that the branch predictor has learned. It turns out that when we consider out-of-order execution, there's a larger class of behaviors which you cannot model with branch prediction alone. So we can't understand it with just this model. Instead, we need a more complicated model. So this is my beautiful conception of how out-of-order execution works in a processor. So this giant hexagon of death in the middle is the reorder buffer. On a typical CPU, like Intel CPU, I think Skylake is 224 microops, so it's a huge buffer of instructions. Everything which is in there is essentially going to have its data dependencies understood by the reorder buffer, but not control dependencies and not memory dependencies. So just zooming out so you can understand the picture, there is a place where the instruction is fetching instructions. That is essentially in the future. So through a chain of predicted branches, the processor has an idea of where it's going to be executing in the future. Those things are getting essentially hoovered into the reorder buffer. And then there's a place where it kind of now is, where it knows for sure that the branches that it's executed have resolved correctly, and those are being committed. But in between these two, there's like this giant warp bubble of instructions where the only dependencies inside are data dependencies. Does this diagram kind of make sense? Just kind of think of this thing moving forward in time. It's moving through the program like this, fetching new instructions in and committing them behind. But inside is going to execute them out of order. Okay, so instructions or microops in the buffer have state, so they can be executed, they can be ready. Executed means that their operands, their data operands have actually been computed, and they've computed, they have a value, they're done. But they're not committed yet because they haven't gotten essentially to the top of the reorder buffer. And then there are instructions that are ready, so all of their operands have been computed, but they've not actually been executed yet. So I wanted to explain what the green arrow means. So imagine the green arrows actually carry over from one slide to the next. So imagine the green arrows are the execution path. What that looks in the reorder buffer is that there's actually branches in the reorder buffer that are kind of threaded through. It's a horrible color scheme, I'm sorry. Okay, so this is going to be an approximation of how branch prediction actually works. It's a little bit more complicated than a typical processor. But you can roughly think of it as whenever a branch actually finally makes its way to the top of the reorder buffer and it's going to be committed, now we actually know which way the branch did go or should have gone. And if it went the wrong way, that means that everything that we loaded into the reorder buffer based on that branch is just wrong. Like the code just didn't go that way. So the branch actually went here. So what we have to do is we actually have to toss the entire reorder buffer. Everything is gone. It's all wrong. It's all fine. We didn't actually change memory. We didn't change the registers. We clear it all out, and we go to where that branch should have gone and restart fetching, and now the new code will be fetched into the buffer. Questions about that? Because it'll become clear now why it's possible to have variant 4 vulnerabilities. Okay, so inside the reorder buffer, it's a giant soup. It's essentially a data flow graph. But the data flow graph does not capture memory dependencies. So if we have loads and stores, it actually doesn't know you can roughly think that it doesn't know which order they came in the original program, which means that loads and stores can be reordered in memory. We've got this wonderful mechanism that whenever we get here, we can figure out whether we did something out of order, but in the middle, it doesn't really know. Okay, why is that going to be a problem? So when we reorder loads and stores, and we do it incorrectly in speculation, there's going to be an information leak. So if we think about just two instructions, we've got a store, apologies for the machine code, that should have been source code. But imagine we have a store and we have a load. If they don't alias each other so they're to completely non-overlapping memory regions, it's absolutely fine to execute them out of order. If there's no fence instruction in between, it's totally fine, right? So we can reorder them, no problem. So when we do this in the processor, we might just show the diagram here. So we're taking this store and we're going to execute it after the other load. That's totally fine. Again, if they're not aliases, if there is an alias, then whenever we execute them out of order, the load, which should have happened after the store, it should have seen the value of the store. But now, since it's being executed before, it sees some stale value from memory. Now, it may be that the stale value from memory had something sensitive in it. So now you've loaded from memory something that you shouldn't have seen because it should have been overwritten. In program order, we literally said store here, load here, but in speculation, we saw what was there before. That's a problem because then we can do our disclosure, right? Now we have a gadget where we can read from memory that we should have not been able to read from because it should have been overwritten. That's a real problem if we can put a pointer there. So maybe that location in memory is something that should have been overwritten by a safe pointer, but there's actually an unsafe pointer there. And now we're actually created one of these universal read gadgets. Other questions about that? This is a pretty simple little gadget. Okay, so this is actually horrible. So it turns out processors speculate on reordering memory loads and stores all the time. They actually have some learning inside to determine whether or not two loads and stores will actually alias each other. But if that prediction is wrong, then you get this potential vulnerability. So we thought through this multiple different ways, and how could this be a problem for code that we generate, and how could we generate code to mitigate it? So just let me walk you through how this could be a problem. So imagine you're the back end of the optimizing compiler, and you spill something to a stack slot, and you spill it like what should be a pointer value, but what was there before that stack slot was actually an integer from another frame. And now, if you load that stack slot back out as a reload from your register allocator, because of this vulnerability, you may actually get an integer from another frame instead of getting the pointer that you should have got. So now you have a way to create a little gadget where you can write an integer and it be picked up as a speculative pointer, and now you can read anything from memory. So imagine how you would mitigate this in the back end of a compiler. You have to make sure that your spill slots never alias in a way that you could have a user's integer be interpreted as a pointer in speculation. And that's essentially means throw away your compiler backend, do it over. Like separate everything by type. Then actually just go one step further. Think about every memory location in your program. When you write to it, you may not get the value that you wrote. You may get something that was there before. For every single instruction in the program, every single store in the program. We were not able to effectively think through this mental model, so we were not able to come up with effective mitigations for this vulnerability. Anybody have other ideas how you might deal with that? Okay, so going back to this list of microarchitectural state, this picture looks a little bit more like this. Every single one of these things that we've looked at, and actually I didn't get a chance to update my slides, but now from last week we know there's a vulnerability there and there's a vulnerability there. So every single one of these things leaks information. Yes?
So which one affects, does zombie load affect?
Zombie load, I think, is the store buffer. It may be one of these two. I forget because I only know our internal code names. It was one of these two. Okay, I'll just mention each one of these. So the model-specific registers, this one's just near me, so I just picked this one. Model-specific registers, turns out that that's a privileged instruction to read a model-specific register. And if you try from user space, you should get a fault. But if the fault happens too late, guess what? Processor just gives you what was there, and you can just disclose that through a side channel if you like, right? So you can effectively read the system registers. The return stack buffer, which I mentioned before, is this little cache of the call and return the return addresses for when you do procedure calls. When you hit the ends of that buffer in overflow, you may actually get a prediction from another one. So it's kind of like variant 2 in that your program speculatively takes a completely wrong turn. And if you do that just right, now you can cause the processor to execute some random gadget, right? So this return stack buffer could also be a vulnerability. There's actually a paper about that. Okay, we talked about the branch predictor state. There's also a vulnerability, just a regular information leak. This is not a Spectre vulnerability, but with the TLB, it turns out that like which memory address you touch, also the speed of that touch also depends on the TLB state as well. So if you probe things in just the right way, you can figure out what the memory layout is at the physical address level. So that's kind of bad because address space randomization is one of a security mechanism, and that can effectively be reversed. So I mentioned the DRAM line buffer. So rowhammer, which is something from 4 or 5 years ago, that all has to do with the electrical characteristics of the DRAM. You can flip bits in memory just by reading and writing nearby things. It's kind of terrible. So page tables as well. Turns out, so I think it was about June of last year, maybe it was a little bit later, one of these Spectre variants actually absolutely has to do with page tables alone. So page table entries could actually be misinterpreted by the processor, and you could read everything in the L1 cache because there was some check that should have happened synchronously and it was asynchronous. Spectre variant 4 I talked about. Turns out also the execution ports, which are the things which are actually executing those little micro ops in the reorder buffer. You can get information about what the other hyperthread is doing depending on what is fast for you. So you can tell what's in the execution ports. And I mentioned the lazy the floating point state, because of that lazy restore, again, in speculation, at least on Intel chips, if the FPU registers weren't actually there and the operating system should go get them for you, in the meantime, why don't you just have what's there, which is what another process is FPU registers, which is kind of bad because that's where you put your crypto keys. Yeah.
So most of this is Intel x86, right? So what about other vendors and other architectures? So R, for example, does it kind of also have these vulnerabilities or not?
Yes.
For the sort of big items like V1, V2, and V4, essentially every processor that does branch prediction, indirect branch prediction, and memory disambiguation, they all have some vulnerabilities like that. A lot of these other things are mostly Intel CPUs. It has to do with the way they implemented faults. But AMD CPUs also have classes of these as well. Yeah.
So now that it's become clear that this microstate is observable and it's causing problems, have you guys, I guess at Google, had any luck convincing vendors to document this stuff better? Or is this sort of thing where this information might be competitive compared to other vendors making the optimization?
It's a complex situation. I think the world is still on fire, and ultimately, so I won't speak specifically to vendors and things like that, but you're right, better documentation would be great so that we know what is in the microarchitecture, and the only way to get there that I see is to have open hardware. Vendors are not super on board with that idea, so I may be in the minority. I'm not entirely sure whether better documentation of the microarchitecture would make things better or worse right now.
Yeah.
Considering it takes maybe 5 years to really significantly change the hardware, better documentation may just mean you get to see vulnerabilities sooner. People are searching for vulnerabilities by the hundreds these days.
Also make it easier to come up with mitigation.
No. Unfortunately, like we know everything. I know way more about memory disambiguators than I should, still can't fix it. Yeah.
Isn't that something like common in the security world that's everyone agreed some time ago that it's better to have like open documentation so that the good guys find it
Yes.
before the bad guys that will never tell the world about it?
Yes. This is why I said I don't think that it would help right now. In the long run, I think it would help. But the problem is there's about 10 billion chips out there that have these vulnerabilities. We have to do this in a responsible way. Yes?
So, given that new attacks on hardware are being found, I mean, not every day, but now they're more and more frequent, wouldn't it be much better, as in the long run, to just say, okay, we'll just switch back to 486 or 586,
Yes. Actually, I think simpler is better if you're in a security-conscious domain. The good thing is that we don't have to go back to 486 clock speeds because we have better process technology, so we can at least run much higher clock speeds. But absolutely, like if you have a security-conscious domain, it may make sense to have a much simpler processor design because, as you see, all this hidden stuff, hidden state is side channels essentially guaranteed. Yeah.
So Intel's trying to get like, you know, up to the next get to 3 gigahertz in 2004. But the performance even with 3 gigs was still terrible eventually. And they had to make use of, improve on out-of-order execution, branch prediction, etc., in order to get even better speed and, performance gains.
I don't know if I would characterize the performance as terrible.
No, they consumed a lot of power. The performance gains were negligible, so to speak.
So there's lots and lots of variables involved. So one is process technology. Process technology has kept advancing at a pretty steady speed. So they can get lots and lots more transistors, which means lots and lots more cache. That's one big thing that's made processors better, bigger reorder buffers and things like that. But to fill the reorder buffers, you need to do lots and lots more stuff like this. So there's like, yes, in general, you need to do more of sophisticated microarchitectural things to actually make those 3 gigahertz count. But there's lots and lots of confounding variables. It's not entirely clear if we chop off huge parts of this how bad it will be.
Yeah, but do you know if anyone has started the exercise of going back through all the architectures and trying to figure out which of them are vulnerable in known ways and how far back you would have to go? Branch prediction is from the mid-60s.
Yeah. I don't know of anybody. Right. I don't know of anybody that specifically started this exercise. I thought about this for some time, and my guess is, because it really has to do with, is your speculation window big enough to fit a gadget? And is that, which you need a certain size of reorder buffer, and you need to be able to create branches that are slow enough.
So does it even need after order execution?
No, not for variant 1 and variant 2, although it helps a lot. Because with a pipeline to architecture, you can only get so far ahead with the instructions that would be in the speculative branch. It helps a lot to be out of order.
Okay, so maybe there's some minimum pipeline depth.
Yeah, I think it would be. Yeah, my guess is that you already need to be at 20 stages before you're into this game.
Okay, so we're talking around 2000. Yeah.
The other thing is that, I worked a lot on making proof of concepts for this. These things are really squirrely. To really make a reliable gadget, you have to make a really slow branch. And to do that, sometimes you actually tie up processor resources that you would need in the speculative, in the misspeculated path. So it may be just, things just don't line up right, even though it's technically possible. Yeah.
So the title of your talk was what Spectre means for language implementers.
Yeah,
I'm getting that.
I get to know.
Excellent question, because it's probably on the next slide. Okay, yeah, I'm almost finished. Basically, this is what it means. Using different mechanisms, including mispredicted direct branches, mispredicted indirect branches, variant 4, all of that. Somebody can, no matter what your language looks like, you give them a timer of any resolution, you can write a well-typed procedure that does that reads all the memory in the address space in which it's running, in any language. If you don't have a timer or access to any non-determinism at all, maybe that's not possible, but that's not realistic. And it all has to do with side channels in the entire address space in which it's running, which means that if you're running untrusted code in an address space with some secrets, you're in for a world of hurt. So what that means is basically, we kind of always knew that this abstraction boundary that was here leaks a little bit, not only because things crash and stuff like that, but the side channels really allow you kind of to see this wireframe mode where you can see through the walls. And that's kind of bad now. That's actually really bad because this boundary and this hardware is really hard to fix. It takes a long time scale, and it's at the very bottom. So everything above it has now got vulnerabilities. It's kind of the worst possible situation. So what we did for securing the web and for Chrome is basically we already had an effort to split different origins, so different sites, into different processes in Chrome. Just because there's lots of other potential bugs in Chrome and many just regular out-of-bounds reads and writes and potential for security problems. So we call that site isolation. All of the browser vendors are also working on their variants of site isolation and have also deployed mitigations, but Chrome has basically decided that JIT mitigations and relying on the JavaScript VM to actually give you memory safety to defend you from untrusted code is not tenable. So defense in depth, process around all the stuff, don't put anything in that process which it should not be able to read. Unfortunately, some platforms, we don't have enough memory to do full site isolation, so all of the JIT mitigations that I talked about are turned on those platforms. So all the other browsers, I can't really speculate on when those will be finished, but they're all working to ship site isolation. We all realize that this is the only viable way to defend against these attacks. Okay, so this is what it means for language designers. CPUs, just full of holes. They're just absolutely full of holes because of branch prediction and because of out-of-order execution. Safety checks in your languages just are completely ignored in speculation, and stuff leaks out through side channels. All the microarchitectural details that you could possibly imagine, you could probably read them now. There's probably a way to do that, which not only is an information leak for programs, it's also an information leak for intellectual property. So you can essentially reverse engineer CPUs if you are dedicated enough and have enough time. So programming language implementations cannot really establish confidentiality like we all believed 2 years ago. And it's possible to just write this universal read gadget in any language. It may take you weeks and weeks of staring at machine code to do that, but it's possible. It's fundamentally not impossible. So you shouldn't run untrusted code in the same process where there could be secrets that it could steal. Yeah?
Part of the problem, for instance, Linux and probably other operating systems are forced to still map to memory their own code to every process for like system calls and so on.
Yeah, they've moved away from that. So because of Meltdown, which I didn't cover because it's kind of out of the browser game, essentially operating systems are moving to a model where they do not map themselves into user address space, even their code.
So my question was, how much can they actually do on a language compiler level? Because all those mitigations that you mentioned basically assume that the attacker has no control over the compiler, right? So if the attacker ships an executable and they can use whatever compiler they want, they could just use one without those mitigations. So it basically mostly applies to languages like JavaScript or maybe some interpreted languages.
Well, any language where you have a virtual machine would be in this game. So Java, and for example.
I have a question for. So early on, you said, I think it was in the first V1 and V2, that basically this was all about if there was a language safety property that was enforced by a dynamic check, it was vulnerable to the branch prediction. But it seemed like, and you sort of said a similar thing in your final slide, from what I saw, but it seemed like actually it's much bigger than that. Even if it's statically enforced, like the memory disambiguator attacks still apply.
Yeah.
Okay. Any questions?
So another question is, if you were, crypto, if you were a developer and you're running crypto code, so given that, Spectre, meltdowns, and so on and so forth are a thing, I mean, you don't know what's harder, but so what are you supposed to do now, effectively, to make sure that, nothing is leaked?
So I would not put high-value secrets in the same process with untrusted code. So if you're doing crypto and you're also running an interpreter where you're getting untrusted code or a JIT or whatever, that's a really bad idea. Just don't do that. So move the crypto keys to another process that only, like, use the principle of least privilege, move it to a process that only does the thing which is necessary for the crypto keys, and don't have a Turing programmable system.
You say, isolated processes, but given that Spectre can read from arbitrary memory.
That's not true. That's not what I said. So within the same address space. So if a process boundary, whatever is mapped into that process, then you can read that. So if the process boundary holds, which it, pray to God that the operating system vendors can do this, then you can't read across processes, even with Spectre.